One strange feature of trig functions is, since they're all ratios of three sides in the most important diagram, there are lots of hidden relationships between them that aren't always immediately apparent. Just for an example, let's think about tangent of theta. Now, the definition of tangent of theta is y over x, but it turns out that tangent of theta is also equal to sine of theta over cosine of theta. Let's check that this is really true. Well, so right now, I'm claiming that this is true, but let's actually check. On the right-hand side, what is sine of theta? Well, in this diagram, sine of theta is y over r. And what's cosine of theta? Well, that's x over r. But then you can simplify this big mess by multiplying the numerator and denominator by r, and you get y over x, just like I said you should get. So this really is true. Tangent of theta really is sine of theta over cosine theta. Now, it looks like this is an equation, and we're used to solving equations, but that's not what this is. An equation that you would solve is an equation that's usually false, but sometimes is true. And usually the game that you play with an equation that is only sometimes true is you try to find the value of the variable that makes the equation true. So, for example, if you were solving for x squared equals 1, you aren't saying that x is always equal to 1. You're saying that there are some values of x that make this equation true, and then you try to find what values those are. And that would be plus or minus 1 for this particular example. This equation, tangent theta equals sine theta over cosine theta, and that's not the kind of equation that this is. This equation isn't sometimes true. This equation is true for all values of theta. So this is true for all theta. We aren't saying this is true for some values of theta and we would like to know which theta. This says that tangent of theta is always true to always equal to sine theta over cosine theta, no matter what angle you put in here for theta, as long as you put in the same angle in these three places. This kind of equation that's true not sometimes but all the time, this kind of equation is called an identity. And since this is an identity of trigonometric functions, it's called a trigonometric identity, or trig identity for short. And there are a few trig identities that we've already encountered, and we will encounter many more over the course of the quarter, but let me just write out a few that we've seen so far. So we know, well, there's the one that we just figured out. Tangent theta is sine theta over cosine theta. I've mentioned sort of offhand a couple times that secant theta is just the reciprocal of cosine. That means secant theta is 1 over cosine theta. And that's always true for any value of theta, so that's an identity. Similarly, cosecant theta is the reciprocal of sine. That's an identity. And cotangent is the reciprocal of tangent. So these are all identities because they're true not for some values of theta, but for every value of theta. There is one more important identity that we have sort of figured out so far, which is if you're in a unit circle, then the coordinates of this point are cosine theta. If theta is the angle down here, the coordinates of this point are cosine theta comma sine theta. So sine is the y coordinate of the point, and that's this green distance. X is the cosine theta is the x coordinate of this point, and that's this blue distance. And because we are in a right triangle, we can use the Pythagorean theorem. The Pythagorean theorem for this triangle says that, for this right triangle, says that x squared plus y squared equals 1. But remember, x is actually cosine theta. So cosine theta squared plus, and y is actually sine theta. So sine theta squared is equal to 1. So cosine theta squared plus sine theta squared is always equal to 1. That's not totally obvious from the definition of sine and cosine, but it does happen to be true. It's just another way of saying the Pythagorean theorem. So this is another identity. It's true for every value of theta, not just some values of theta. This is usually called a Pythagorean identity. Pythagorean, because it came from the Pythagorean theorem. Incidentally, just a quick note on notation. Usually, if you have a trig function raised to a power, you don't write the power all the way out here to the side. It's sort of traditional to put the exponent right next to the trig function. It means the same thing, it's just a different way of writing it. You will see this. This is pretty standard notation, so you will see this in books of all varieties that use trigonometry. All right, so in addition to these reciprocal identities over here, we also have this Pythagorean identity that cosine squared theta plus sine squared theta equals 1. There are actually two other Pythagorean identities that look kind of similar, and you can get them just by playing some cheap tricks with this first one. So for example, if we divide both sides of this by cosine squared theta, on the left-hand side, we get cosine squared theta over cosine squared theta plus sine squared theta over cosine squared theta equals 1 over cosine squared theta. Okay, well this first piece is really just 1 plus the second piece, since the numerator and denominator are both squared, you can take that squaring outside. So this is sine theta over cosine theta, all squared. And you can actually do the same thing on the right-hand side. It's 1 over cosine theta, all squared. That means we get 1 plus sine theta over cosine theta. Well, that's just tangent theta. So we square that. So tangent squared theta. And on the right-hand side, 1 over cosine theta, that's secant theta. So this is secant squared theta. So here's another Pythagorean identity. It looks kind of like the one with sine and cosine, except the 1 is in a different place. So it's kind of tricky to remember which side this 1 ends up on. So usually what I do is I only remember the one with cosine and sine. That one is sort of deeply ingrained in my memory. And then I just remember that if I need to, I can divide by cosine to get this other Pythagorean identity. You might not be surprised to find out that if you start with the sine and cosine version of the Pythagorean identity again, so let me back up. I need to erase to give myself a little more room. If we start with the sine and cosine version of the Pythagorean identity, that's cosine squared theta plus sine squared theta equals 1. If we divide everything by sine squared instead of cosine squared, and on the right-hand side as well, then we get another Pythagorean identity that looks a little bit different. So cosine squared over sine squared, that's cotangent squared theta. If you don't see why, take a second to figure that out. Sine squared theta over sine squared theta, that's 1, equals 1 over sine squared theta, that's cosecant squared theta. So there's another Pythagorean identity. So there are 3 versions of the Pythagorean identity, one with sine and cosine, that's the most important one. and then one with tangent and secant, and one with cosine and cosecant. All right, so let's look at an example of how we can use these identities. First example, so let's suppose that sine of theta is negative 3 over 5 and cosine of theta is 4 over 5. Let's find cotangent of theta. Well, we could draw a most important diagram with this sine and cosine, but let's use identities instead. So cotangent, you might not remember immediately how it's related to sine and cosine, but hopefully you remember that it's 1 over tangent. All right, well, that doesn't help immediately because we only know about sine and cosine, but hopefully now that we have a tangent, you'll remember, oh wait, tangent you can write in terms of sine and cosine. Tangent is sine theta over cosine theta. It's a little bit annoying to have a fraction in the denominator of a fraction, but we can clean that up. So this is the reciprocal of sine over cosine. That's cosine theta over sine theta. And now that we have cosine and sine, we can use the values that we have. So cosine is 4 over 5. Sine is negative 3 over 5. And so we should just simplify this. Multiply the numerator and denominator by 5, and you get negative 4/3. So whatever that angle is, its cotangent is negative 4/3. All right, let's look at another example. If theta is an angle in the fourth quadrant, whose cosine is 3 over 4, then find sine of theta. So again, we could draw a most important diagram reflecting what we know about this angle in order to find sine of theta, but let's use identities. So we know, we know something about cosine, and we're trying to find sine, so we should use an identity that has sine and cosine in it. That would be, I guess, the Pythagorean identity for cosine and sine. So cosine squared theta plus sine squared theta equals 1. And we know what cosine of theta is. It's 3 over 4 plus sine squared theta. And now we can just solve for the thing that we don't know, and that would be sine of theta. So let's see, do this arithmetic. 3/4 squared is 9/16, I guess, plus sine squared theta equals 1. Then we can move that 9/16 to the other side. We get sine squared theta equals, 16/16 minus 9/16, that's 7/16. And then we can take square roots. So sine of theta is, well, wait, when you take a square root on both sides of an equation, you get a plus or a minus. And, this angle is some particular angle. We don't know what angle it is, but it's some particular angle. And so its sign should either be positive or negative. It can't be both. So let's think a little bit more about this angle. It's an angle in the fourth quadrant whose cosine is 3 over 4. So let's draw a picture of what that would look like. So here's a unit circle, and the fourth quadrant is down here somewhere. So there's our angle theta. In the fourth quadrant, well, remember, in this unit circle diagram, sine tells you the y coordinate, and in the fourth quadrant, this y coordinate is negative. So just based on the quadrant we're in, we know we should choose the negative value for sine here. So for this angle, theta, sine of theta is the square root of, the negative square root of 7 over 16. And, we can simplify this square root a little bit. It's the square root of 7 over the square root of 16, which is 4. All right. One final trick we can play with these identities is it's actually possible to express all of the trig functions in terms of just one of them. So for example, let's express cosine theta in terms of sine theta for all angles in quadrant 2. It is important to know what quadrant you're in because, as we've seen, what quadrant you're in determines whether you choose the plus or the minus when you use these Pythagorean identities. Okay, so to express cosine in terms of sine, well, we're going to need some identity that has them both in it so we can solve for cosine. And an identity that has cosine and sine, yeah, we're talking about the Pythagorean identity again. So cosine squared theta plus sine squared theta equals 1. And now express cosine in terms of sine. That means we want to solve for cosine, really. So let's solve for cosine. Cosine squared theta equals 1 minus sine squared theta. And then we can take a square root. Cosine theta is plus or minus the square root of 1 minus sine squared theta. And as usual, it's the quadrant we're in that will tell us whether we want to choose the positive or the negative here. So for quadrant 2, that's up here in the upper left, in quadrant 2, x coordinates are negative and y coordinates are positive. Cosine is talking about an x coordinate, and so in quadrant 2, cosine should be negative. So we should choose the negative square root here. So in quadrant 2, cosine theta is negative square root of 1 minus sine squared theta. All right. Notice that because we had to take a square root to express cosine in terms of sine, this identity actually isn't true for all values of theta anymore, but it is true for all values of theta in a certain range, any value for theta that happens to put you in the second quadrant.